In this video you will learn how the Laplace transform turns differential equations into simple algebraic equations. We start with a time function f of t that describes a signal or system state. Our goal is to convert f of t into a function f of s that lives in the complex frequency domain. The complex variable s is written as sigma plus I omega, where sigma controls exponential growth or decay and omega captures oscillation. The Laplace transform is defined as the integral from 0 to infinity of e to the minus st times f of t with respect to t. The lower limit 0 reflects causality. We only care about the future response of a system that starts at time 0. The upper limit infinity captures the entire future evolution of the signal. The factor e to the minus st can be split into e to the minus sigma t multiplied by e to the minus I omega t. The real exponential damps the signal so the integral converges, while the complex exponential encodes frequency information. Visually you can think of the exponential kernel as a sliding weight that gradually shrinks the contribution of f as time moves forward. Now let us explore the basic properties that make the transform useful. Linearity. The transform of a sum equals the sum of transforms times shifting. Delaying by a constant a multiplies the transform by an exponential. Scaling stretches the s variable. Differentiation in time becomes multiplication by s minus the initial value, and integration becomes division by s. Let us compute two elementary transforms first. F of t equals 1. The unit step, the integral becomes the integral of e to the minus st. Integrating gives negative 1 over s times e to the minus st from 0 to infinity. At infinity the term goes to 0, and at 0 it is 1, leaving 1 over s. Second, f of t equals t. We integrate t times e to the minus st. Using integration by parts, we eventually find that the transform is 1 over s squared. Now we solve an ODE. Y prime plus y equals 1. With initial condition 0, transforming both sides gives sy of s plus y of s equals 1 over s. Factoring and solving for y of s gives 1 over s times 1 over s plus 1. We then use partial fractions. The inverse transform yields the solution y of t equals 1 minus e to the minus t. We solved the equation without integration in the time domain. Not every function has a transform. It must not grow faster than an exponential. Also, remember that s is a complex variable, not just a simple number. In summary, the Laplace transform is a powerful tool for linear time invariant systems. Converting calculus into algebra, use it for circuits, vibrations, and control systems. Generate your own educational videos for free at eduvids.vercel.app.